So before we go on to prove a lemma that will help us prove the LSZ theorem, let's discuss the general assumptions that we have to adopt in order to prove the theorem. So we are working in an interacting quantum field theory, but what we're going to assume is that our particles are asymptotically free particles. That is, our particles asymptotically are non-interacting. In other words, we are assuming that the interaction is turned on for a finite interval from minus t to plus t. Now, because we are working with an interacting quantum field theory, we cannot assume for all time that our quantum field will have a Fourier mode expansion which is similar to the Fourier mode expansion or identical to the Fourier mode expansion that we saw in the free quantum field theory case. Recall that in the free quantum field theory case, if we took a field phi of x, then we could write it as an integral over the Fourier modes where it would be a linear combination of the annihilation operator with the coefficients been given by plane waves. These are the positive modes and the negative modes. Would be of this form. So in general, for interacting quantum field theory, we cannot assume that this is true for our quantum field at all times. But for a specific time, say time t equals to, say t naught, we can assume that our quantum field can be expanded as a Fourier integral where we have the creation operators and the annihilation operator. So what we can assume is that we can assume this form only at a very specific time. So I'm actually just writing the same formula again. But this is only valid at a very specific time, t equals to t naught. So because we're in the Heisenberg picture, we have to ask the question, what is phi of x given its value at a specific time? What is the value of phi of x at some arbitrary time? So here we are assuming t is equal to t naught. So given this, phi of x at arbitrary time is defined to be the time evolution operator in the acting on phi of x at time t equals to t naught in this fashion. So this is what we actually mean by a Heisenberg operator. So now what we can see is that if we define ak of t to be e to the power I h t minus t naught, a of k e to the power minus I h t minus t naught, and a dagger of k t to be e to the power I h t minus t naught, a dagger at k e to the power minus I h t my t naught. If you define this, then we can write phi of x at arbitrary time in a form that looks similar to the form that we're familiar with from the free theory. So instead of having the creation operator, which is independent of time, and the annihilation operator, which is independent time, here we have a creation and annihilation operator, which is dependent on the time, and a creation operator, which is dependent of the time. Now, one thing to note is that what we don't know is that how these operators, how they are related to the ak t naught, which is of course our name for a of k. We don't know in general how these are related because our operator is an interacting quantum field theory Hamiltonian, and working out this relationship in general is going to be non-trivial and perhaps even impossible. So in some sense, this is just a definition because all the complication of this formula is now contained in these definitions. However, given this, what we are assuming is that asymptotically the interactions turn off, and that asymptotically, these operators, a dagger of k at minus infinity, they create the states which go into our in state, and a dagger of k at plus infinity create the states that act as our out state. In other words, we can write our in state, or something that we are calling in state, as a dagger k of a minus infinity and a dagger k of b at minus infinity acting on omega. And our out state is going to be a dagger k 1 at plus infinity dot 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 a dagger kn at plus infinity acting on omega, such that our S matrix element, which is say our S matrix element is the final S initial, will be given by this thing, and which is omega. We are taking Hermitian conjugate of this thing now, and here we have, because of the Hermitian conjugation, the ordering of the operators will be changed, and the daggers will become undaggered. And then for the other ones, we have a k of a dagger at minus infinity times a of kb dagger at minus infinity acting on the vacuum. So this is our expression for the S matrix.